So, hello. I realized I brought the wrong talk because it's mostly about the tooling and less about the application in my case. We are working in lumped system models, so or cardiovascular flow simulation. So I traditionally have done 3D simulations for ages in moving hearts, in arteries. Recently, my focus is on atherosclerosis risk prediction. So on the right, you see a result in a murine aorta with wall shear stress and oscillatory wall shear stress. And I'm dynamically switching to talking more about the application and less about the tooling now. So the thing we're looking for is damage to the endothelium, which is caused by the flow patterns in this. If you have high wall shear stress, that's protective, but if the wall shear stress oscillates, that kind of confuses the cells. They don't know in which cell direction they need to align, and you get a disturbance in the cell layer that lines the arteries, and you end up with an atherosclerosis lesion at that point. So the prediction of these, I don't use Julia for this maybe yet. My code is written in OpenFOAM. But what I need for these simulations, because we can't model the whole body or the whole circulatory system with these 3D models, is we need good boundary conditions. So we need to know what the pressure response at each of these branches is, and that is usually done with a Windkessel model, as we've seen in the previous talk, and I'm going to show one in the next few slides. And we always have the inverse problem there. So for Windkessel model that only has 3 parameters, that's not that much of a big deal, so there was not a lot of pressure for me to move to Julia. But when we move to full circulatory system models, and on the right you see a model of the full circulatory system, we have the heart in the middle, which is modeled as 4 chambers that contract. So you have elasticity functions that are time dependent or can be coupled to an electrophysiological model of the heart. So we get the polarization, depolarization waves running around the heart, which makes the muscle contract. So if you can model that, you can put that as an input function into these models. And then suddenly for this rather simple model, because all we have here is a systemic circuit here, so we have the left ventricle, the aortic valve, then it goes into the systemic aortic sinus, which is in a Windkessel model modeled as a compliance, which is the extensibility of the vessel, so the ability to store volume and to dampen out the waveform. So we go in with a waveform like that, and we come out with a waveform that is flatter, and the volume over time is obviously the same, but we flatten out that waveform, so that's what the compliance does. We have a resistance, obviously, and we have an inertia term. So we have the inertia in the blood, which is important in the larger vessels, and then as we go down the tree into the arterioles and the capillaries, we go down to only resistances in there, and then in the veins, it's mostly compliance that stores the volume in your body. And then we go back into the right side of the heart and then into the pulmonary circuit. And this is a relatively simple model because obviously we have more than just one big vessel or 2 big vessels as we have simulated them here. But if you go down, there are models that have 144 vessels down to the capillary bed and then equally many branches coming back. So these models can go big quite quickly. This simple one has, Harry, you correct me, about 88 parameters. And solving the inverse problem on that is an issue. And that's where Julia came in. So for a simple 4-element Windkessel model, I can hand derive these equations. And then I can implement that in Python. I don't want to go through the code. I just rolled to the end to the CPU times, 961 milliseconds for a single run for 20 cycles on this. In MATLAB, code looks, but it's just the same. This is hand-derived equations. I'm down, I can't read that down there. That's about 120, 130 milliseconds now. And in Julia, well, everybody knows this, we're down to 3.7 milliseconds now. So, and the code looks much nicer in my view. But that's not the main issue. Well, the next pressure we had when we looked into what we want to do, which is ultimately finding out which of these parameters have which values, so parameter optimization, classical optimization problem, inverse problem, but also looking into global sensitivity, looking into parameter identifiability, and most recently using Kalman filters to look into real-time assessment of how parameters shift if something happens to the patient. Because these kind of models, these circulatory system models, are used, for example, in extracorporeal circulations. If you have open heart surgery, your heart is basically cut off from the circulation, perfused externally, and your circulatory system is perfused with an iron heart, basically, an external pump. And the parameters for that, how you drive these systems, they very much depend on the parameters of your own personal circulatory system at that moment. So what happens if, for example, you have a volume loss somewhere, bleeding? How does that change all the parameters? How does your circulatory system react? And we need that in real time. That's the idealized clinical application that we're working towards here. And Harry has been working on Kalman filters that allow finding these parameters in real time while the model is running. So we don't even need to go through a global sensitivity analysis problem anymore, a global optimization problem anymore, but we can do that in real time with the speedups that we get with the model. The next thing is we don't want to derive all these equations by hand. Because deriving the equations by hand, you have to go through the Kirchhoff's loops, etc., and then you end up with a lot of differential equations, and then you need to solve or break all those down to a solvable set. And you can do that in, well, n minus m faculty possible ways, and not all of them are the optimal ones. So we went and looked for modeling toolkit, the A-causal modeling system, and developed a library that allows us to quickly come up with new models and derive models, change the model around. So for example, we can easily put a coronary loop in there, which changes the whole topology of the model, which usually would mean sitting down with a couple of mathematicians for an afternoon and deriving the equations by hand again, or 2 afternoons, or 3 or 4, depending. And you get negative signs in the wrong place. I'm great at that. So don't need to explain what A-causal modeling is, I think. What we have, very quickly in here, what we have is the network, which is the topology, and we have components. So the network has connections, and on each connection I need to fulfill the Kirchhoff equations, and the components have their own ODEs coming with them, and they can be quite complex. In particular, when we're talking about ventricle models, pumping chambers, which might even include electrodynamics, electrophysiological models, or with valve models which have their own mechanistic description, which can be 2 or 3 differential equations as well. So we need a way to combine those two. So we have the network models, which gives us the connection equations. We have the equations for the components, which gives us the ODE. So for example, a compliance has a dp dt is q over dq over c. And that is a differential equation that is defined in the component equations, and these are all combined, and then we have a huge system of differential equations, some 140 equations for this system. And then we simplify that, and that's where the magic happens. I have no idea how. Structural simplify takes that and makes 6 out of it, or 8, I think, in this problem. And then it's just a regular ODE problem. So simplify. So we have the connections here for this simple model, for the 4-element Windkessel model, that connect all these together. Here we have the components defined, which are predefined, so you define those once and can reuse them. And then we get a system with, in this case, 32 states, and then that is simplified into a two-state system, which we had before. That's the same system, so we expect those two differential equations. And for some reason, that is even faster than the hand-derived one, namely by a factor of 2. And well, the reason I found is it does not derive the equations in the way I would do it by hand, but it optimizes it for the solver. It's because in this case, I get a mixed description in pressure and in volume, whereas most scientists would just derive the equations in pressure, 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 and not, or in volume, 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 but not necessarily in pressure, volume. But these mixed descriptions, as we also know from CFD simulations, are usually more stable in the simulation, so that's where the speed up comes from. So Modeling Toolkit does that for me as well, and I don't even need to think about it, which is great. Because I want the solution to the problem and not thinking about how to make the solver more optimal. So you can use this if you work with circulatory system problems, maybe extend the two-element Windkessel model to a more complex one that is directly usable in these applications. It's on GitHub. We are working on making it compatible with a new system, the new Modeling Toolkit system and the GUIs that are developed at the moment, and hopefully get that into the standard library. So large system then looks like that. If I do that, so for this system, we now are at real time. So this is for 20 cycles. Yeah? So Python uses about 60 seconds for 20 cycles. That's far from real time. MATLAB is now relatively fast with 6 seconds, but they use, and Julia is 170 milliseconds, so that's 17 milliseconds per cycle, which enables us to do the real-time parameter fitting using Kalman filtration in the back, in the future, which we're working on at the moment. We can define new systems by combining things together. So this now takes one of these loops and just makes it into one new component. And then once we've done all that, and that's one of the big novelties that we have now, we're also working on better valve models to simulate hard valve defects. And just opening a diode doesn't do that, so we have mechanistic models that have the dynamics of the hard valve leaflets in them. And if I want to change those and want to change the hard valve description, then usually I would need to start from scratch with deriving the equations, because I changed the 3 ODEs in the whole system, so I would need to start from the beginning. Here, I do that with 4 lines. Well, after I've defined the dynamics in its own element. It's 4 lines to go from one to the other and just change the hard valve representation. So it allows me to do parameter studies, what-if studies, much quicker. And that's one of the things we're working on at the moment. There was a big discussion on CellML on the sidelines. So I put those 2 slides in. CellML is the standard exchange format for these types of models. However, I found it's kind of stagnated in development. I couldn't get the cardiovascular models to work, but we checked CellML runs just as fast in Modeling Toolkit using CellML Toolkit. So that's brilliant. So if I import a model into Julia and run it in Julia, it's just as fast as the native C implementation in OpenCore, which is the CellML solver. And actually, CellML Toolkits, for me, seems to be the best way to run CellML models at the moment, because the CellML toolchain is very old and difficult to get running. And I find Julia to be more flexible. It's more composable, because I can now use these models with all the SciML framework, optimizers, sensitivity analysis, and everything else. So the only key disadvantages that I see with Julia over CellML is it's not as well established yet. We're working on that. And units is one big missing thing. I think when we talk about clinical acceptance of these models, the clinicians want the units embedded in the model, and I think that's been clear yesterday in the discussion that we need to work on that as well. So thank you very much.
Thank you very much, Torsten. Are there any questions from the audience? Yes, Julia.
Thank you very much. Very nice work. So I have a question, a little bit maybe not exactly related, but we were interested in kind of similar work, not for hemodynamics, for the interface of electrodes with the cardiac tissue. Mm-hmm. And we have a lump models there, and some of the elements are not linear models. Basically, they are CPE models with the constant phase elements, which are like capacitors, but they don't basically, they are not 90-degree capacitors. They are not well defined by differential equations, so they need lots of algebraic equations. So have you had experience? I mean, it seems that we can use your basically circulatory model for this kind of non-linear elements. That would be very nice thing for us. I don't know how much that's possible.
So if I understand it correctly, the question is how easy is it to get elements into a modeling toolkit that are not a simple ODE?
Basically,
yes. The valve models are a good example for that, because the valve dynamics themselves are ODEs, but there's also a lot of constraints. In our valve model, we have the dynamics of the heart valve leaflets, so we need, and we describe the opening angle as an ODE, and then from that we get the opening area and calculate the resistances dynamically. So all of these equations, it's a very mixed ODE algebraic equation description, so that should work. And the other thing that we had to do in these, which causes a bit of a problem with automatic differentiation, is we have dynamic callbacks in there which catch events. So if the valve approaches its maximum opening angle, we need to do something, and we need to change the speed of the omega. So we need to directly switch omega off via a callback, and that's an event that most systems will have problems with. Modeling Toolkit, surprisingly, or maybe not, I don't know the internals, the solvers are extremely stable against that kind of event. If you look at that solution here, you see these wiggles when the valve closes. Yeah? That is because the publication we followed when we implemented that heart valve had the opening, and it has a maximum opening, and so when we approach that, it's a rigid hard doorstop, so to speak. So the heart valve runs into that, and we get an impulse response, which is not physiological, but it's in the model, and usually that's something that upsets ODE solvers quite a lot. That simulation is done with a 7th order Runge-Kutta, that's Wern 7, but we went to Wern 9, and we don't need a stiff solver for that in differential equations JL, because the event handling slows down around that point enough to get a really fast solution. Okay, we get slower solution with these models than with the simpler valve model, but it still is able to cope with that basically Heaviside function in omega quite well, or very well, because a 9th order Runge-Kutta with an impulse response like that being stable is, well, I think remarkable.
But I've also got nonlinear capacitors, nonlinear resistors
that
are published in literature already. They're not in the package yet, but I've got them working.
And they work well as well. So nonlinear elements is definitely possible.